of the soil structure interface has great influence on the calculation results of dynamic system. So it is necessary to deal with the interface problem reasonably and give the reasonable contact surface condition. And there are some famous joint surface elements. For example, the first is a hyperbolic model developed by Clough in 1971. The second is SSI model developed by SSI in 1992. And there's a Chinese scientist developed an IN model in 1994. And the fourth is SSI model is 23, developed by Viscous. And now, usually we used these two joint surface elements in some famous software. The joint surface element, there are two were introduced. The first is Goodman element. Another is the thin layer element. First, let's see Goodman element. It's a joint element and a no thickness element. Then we can use this element to simulate the contaction between the soil and the structure. And here, this is the description. This figure is a description of the element. And although there's no thickness of this element, but totally they have three. It has four nodes. Node 1, node 2, and nodes L, K, I, J. One side is soil, another side is structure or concrete. And there's two springs. One is provide the normal force, another is provide shear force. Then now we create a stress vector, include two components, normal stress and shear stress. Then this is the displacement vector, include the normal displacement and shear displacement. Then we can create the stiffness equations. Stress equal to stiffness matrix times the displacement vector. And this is this stress and displacement belong to the one element. Then we use upper script E here. Let's see. Now let's see the stiffness matrix. Only Kn and Ks is normal direction stiffness and shear direction stiffness. And we define it as Ks and Kn are tangential and normal stiffness respectively. The key is how to determine the spring stiffness coefficient accurately. And the spring between two contact surfaces bears the action of normal stress and shear stress, and the relative normal displacement and the relative slidings is a tangential displacement occurred between the contact surface. That means L and K will move horizontally relative to the node I and node J. Let's see. Another one is the SSI thin layer soil element. For example, upper element with full nodes belong to soil, and the lower elements with full nodes belong to concrete. Then we can find a joint element with a YB, and it has a thickness T here. Then the stiffness matrix include DS, DSN, DNS, and DNN. The thickness is T, and the length is B here. This is now we say is length. This is a stiffness matrix, and the normal components and the tangential components are considered separately. Then Clough and Duncan proposed a nonlinear elastic model of contact surface when the pressure in contact surface normal stress sigma n larger than 0. Then KSS equal to Ks times the gamma W and times the sigma n normal stress over Pa, the pressure of air poured n times the 1 minus Rfs times tau over sigma n times the tangent delta S plus Cs square. And Kn equal to 10⁶ MPa. We can find that this is a very large value. When the pressure in contact surface normal stress sigma n less than 0, then Kn and Kss equal to 0.01 MPa. And in this condition, I think the stress is a tension stress, a negative value. Then there's the stiffness is very low. When gamma W is unit weight of water, and Pa is air pressure here in the equation. And the infinite fields and artificial boundary problems. When analyzing the interaction between soil and structure and the static load, the soil boundary can be intercepted far away from the structure, and the problem can be directly transformed into the analysis of the system composed of structure and finite element, finite soil. Therefore, the dynamic interaction between the soil and the structure, the virtual boundary will reflect the wave radiated from the structure back to the finite soil, which has been intercepted, so that the wave cannot pass through the virtual boundary and radiate to infinity. Therefore, the finite soil cannot be simply intercepted for analysis. Artificial boundaries are set on the intercepted boundary, artificial transmission boundary and artificial damping boundary, and so on. The energy exchanged between the intercepted finite soil and the external infinite soil can be carried out. And the rigid boundary is used to put the design ground motion, input the acceleration time history. And our intercepted boundary are taken as artificial boundaries, and the ground motion is input at the bottom boundary. This is input stress wave times history. Even ground motion input, the ground motion input considering traveling waves effects. That's the motion on the artificial boundary consists of the known incident wave and the scattering wave generated by the foundation of the structure. So the scattering waves is absorbed by the artificial boundary, and the incoming radiation wave must be input into the calculation area by a certain method. Since the input problem is transformed into a wave source problem to deal with the wave input, the superposition principle of the force is satisfied. The incident wave field and the scattered wave field on the artificial boundary don't affect each other. So the incident wave field and the scattered wave field can be treated separately. And these boundaries are usually used. First is viscous boundary. The basic idea of the viscous boundary is simulate the influence of infinite domain by a boundary force. That is, the normal force equal to negative rho, the density of the soil, and the Cp, that's the viscous coefficient of P prime times the P prime velocity, P wave velocity, and shear stress equal to negative rho, density of soil, times Cs, the viscous coefficient of shear times the S wave velocity. VNVS, that the velocity of particles in the normal and the tangential direction respectively, and the sigma n and sigma t are the normal stress and the tangential stress acting along the viscous boundary respectively. This is a viscous boundary. The second type is a viscoelastic boundary. Here we use a small figure to describe it. It's a parallel connection of a spring and a viscous element. Then it can provide the energy dissipation and the elastic resistance. And in this viscoelastic boundary, the stiffness Kbn equal to alpha n times G over R times A, and Kbt equal to alpha T times G over R times A. And there's a Cbn is same with the viscous boundary. That's the rho Cpa and the Cbt equal to rho Csa. Here Cpcs is same with this with Cpcs, viscous coefficient. And this Cbn and Cbt describe the viscous coefficient is viscous coefficient for this viscoelastic boundary system. And Kbn and Kbn and Kbt are the stiffness of this viscoelastic boundary. For the corner nodes, it has been constrained in two directions with viscoelastic boundary. Let's see the comparison of the viscous boundary and the viscoelastic artificial boundary. Let's see. This is the load acting area from A, B, C. And this load is given with this wave, a triangular shape wave, only one cyclic. Here, let's see the dashed line here. We observe the A response at A point. We can find in the beginning they are same. And if we use viscous boundary, is the dashed line. And the continuous line is analytical solution. And the viscoelastic result is the dashed line close to continuous line. Then we can find, in fact, viscoelastic boundary is reasonable, and is same in the observation at B point. This figure, the comparison of the curves. Here, let's see. For practical engineering, concrete dam, set on a soil. Then we select a zone of soil, and surrounding this zone, we have to apply the boundary element. For example, viscous boundary or viscoelastic boundary surrounding it. And this is the diagram. We cite the boundary at the viscous or viscoelastic boundary at the node in the boundary. And this can let the energy dissipate. Here, the stiffness, we use the same equation, alpha times G over RB, and viscous coefficient C equal to rho times C. Or if another kind of structures, for example, is a building set in the soil, then we select a zone of soil, and in the boundary, we have to use some artificial boundary to describe the transmissions of the energy to the far field. This is the conclusion of the viscous coefficient. When you use viscous boundary or viscoelastic boundary, how to determine the viscous parameters with viscous coefficient and stiffness coefficient. Then let's see the development of soil in soil structure interaction research. And in the 1930s, scientists have to solve the mechanical foundations vibration problems I already introduced in the introduction. in the chapter 1. And in that times, they when they analyzed the vibration of machine, they should consider the effects of the soil. And then after 40 years, in 1970s, the field of protection engineering and earthquake engineering provide development of soil structure interaction. In particular, the development of nuclear power engineering, research on seismic and anti-rot performance of the tall and super large structures. Here we can know that nuclear power engineering. Usually, when we build a nuclear structure, we have built a very heavy, very hard and heavy concrete structures, and any cracks is forbidden in these structures to prevent the escape of the nuclear materials. Then, in the earthquake design, we should analyze the response of this structure exactly. Then you must consider the effects of soil. And another is the research on seismic and anti-rot performance of tall and super large structure. We know nowadays the buildings are very high. Sometimes it's more than 500 meters or 600 meters. And in this condition, the soil effects or soil structure interaction will affect the response of structure heavily. Or some large structure, super large structure with a large contact area between the concrete and foundation and the soil. Then the effects of soil structure interaction is very heavy. When we design or we do analysis of structure, we must consider the soil structure interaction. Okay. And first, the free field response and the structure scattering of the wave. And the action of wave, such as a seismic wave. The movement of soil near the surface of the free field is different from that of the underlying bedrock. On the other hand, the scattering of the wave by structure will affect the response of the free field. First, we can find that the vibration of the soil will affect the response of free field. That is, we define this is dynamic response of free field. And the movement of bedrock cannot be simply regarded as the movement of the bottom surface of the structure foundation. Then that means the input problem of ground motion. Because the foundation, usually we take it as a bedrock. There's a deformation, not a rigid body. Then it will affect the response of upper structures. And in order to determine the dynamic load acting on the structure, it is necessary to solve the dynamic response of the free field and consider the scattering effects of the structure on the wave. Then have to study on the dynamic interaction systems. Because the movement of bedrock cannot be simply regarded as the movement of the bottom of structure foundation. Then first we have to do the free field response analysis. And when you want to do this, we have to develop a free field response analysis method. The free field is simplified as the analysis of horizontal shear motion of the viscoelastic soil column fixed on the bedrock. Then we can use the analytical method. And the loomed mass method is used for the irregular free field with earth dams and embankments built on the non-horizontal ground surface, and the adjacent particles are connected by the shear spring damper. And the complex side, numerical complex side, nonlinear, heterogeneous. Then we can use the numerical analysis method. And we can find, let's see the left picture I already introduced. The upper structure and site on the layered soil and on the above the bedrock. And in fact, in bedrock, there's we can determine the earthquake acceleration time history, and we can do the free field analysis to get the acceleration time history on the ground surface. Step by step, we can deal with, but is deal with. We can analyze the dynamic response of upper structure, but it's not a real soil structure interaction. Then we can use the Penzer model shown in this figure. I already introduced for the upper structure and foundations. And the interaction between the layered soil and the response zone with the far free field. Dispersion of wave by the structure. The vibration produced by the earthquake, pile driving, and underground engineering construction often propagates in the form of elastic wave in nature soil layer. Reflection occurs when an obstacle is encountered. There are three kinds of body waves that can propagate in saturated soil. Faster compression wave, P1 wave, or slow compression waves, P2 waves, or shear waves, include SH waves and HV waves. SH wave vibration direction is horizontal, and S wave the vibration direction is horizontal. And the research on the scattering of the wave by structures includes the influence of discontinuous formed by structure, cracks, and holes in soil on wave propagation. The dynamic response of the structure is not discussed. For example, in the ground there's a valley or there's a hole. When the waves passing this part, and how the waves transmit. The scattering of SH wave and P waves